Hello students, welcome to EPG Pathshala. I am Tanushree Shahadas Gupta, Professor and Associate Dean in S.N. Bose National Center for Basic Sciences in Kolkata. I belong to the Department of Condensed Matter Physics and Material Science. I am also the coordinator of the thematic unit of excellence on computational material science set up within S.N. Bose Center. In this lecture as well as in the next lecture, we will focus on the modern density functional theory given by Hohenberg-Kohn and Sham, which is the underlying theory used in several of the electronic structure codes used by many different researchers. This theory was a significant advancement over the Thomas Fermi method, which was discussed in the previous lecture. This is among the most popular and versatile methods available in condensed matter physics, computational physics and computational chemistry. The number of research papers published based on density functional theory follows a nearly exponential growth as function of the years. Density functional theory was introduced in two seminal papers in 60s by Hohenberg-Kohn in 1964, which has now more than 5,000 citations, and by Kohn and Sham in the year 1965, which has now more than 11,000 citations. This was almost 40 years after Schrödinger published his first epoch-making paper marking the beginning of wave mechanics. Walter Kohn, born in the year 1923, is an Austrian-born American theoretical physicist. He played the leading role in the development of density functional theory, which made it possible to incorporate quantum mechanical effects in the electronic density rather than through its many-body wave function. The Nobel Prize in Chemistry in the year 1998 was divided equally between Walter Kohn for his development for the density functional theory and John Pople for his development of computational methods in quantum chemistry. Density functional theory, which popularly is also known as DFT, has been very popular for calculations in solid-state physics since 1970s. However, DFT was not considered accurate enough for calculations in quantum chemistry until 1990s, when the approximations used in the theory were greatly refined and improved to better model the exchange and correlation interactions. In many cases, the results of density functional theory calculations for solid-state systems agree quite satisfactorily with the experimental data. Computational costs are relatively low when compared to traditional methods such as Hartree-Fock theory or its descendants based on the complex many electron wave function. Despite recent improvements, there are still difficulties in using density functional theory, namely in the description of band gap in semiconductors, description of van der Waals forces, dealing with strongly correlated electron systems, etc. The development of new density functional theory methods designed to overcome these problems by alterations to the functionals or by the inclusion of additive terms is a topic of current research. The original density functional theory has been generalized to deal with many different situations like the spin-polarized system, the free energy calculated at finite temperature, superconductors with electronic pairing mechanism, relativistic electrons, time-dependent phenomena, and excited states, describing bosons, molecular dynamics, etc. With this brief introduction, we now move on to the details of the method. The plan of today's lecture are the following. First, we will discuss the Hohenberg-Kohn-Sham theory, which is the modern density functional theory. In particular, we will discuss the Hohenberg-Kohn theorem. We will discuss the minimization of energy functional, which is the crux of the problem, and the scheme to obtain the kinetic energy functional for the non-interacting system. Following this, we will discuss the Kohn-Sham equations and the self-consistent scheme. In this as well as in the next lecture, we will focus on the modern density functional theory or DFT as given by Hohenberg-Kohn and Sham. This is the underlying theory used in several of the electronic structure codes used by many researchers, as we have mentioned in the introduction. This theory is a significant advancement over the Thomas Fermi method, which was discussed in the previous module, that's module 21. This is among the most popular and versatile methods available in condensed matter physics, computational physics, and computational chemistry, and now also extended to biological systems. Walter Kohn got the Nobel Prize in Chemistry in 1998 for his development of density functional theory together with John Pople. This picture shows Walter Kohn receiving the Nobel Prize from His Majesty the King of Sweden at Stockholm Concert Hall. As we have mentioned in the introduction, the number of research papers published based on density functional theory follows a nearly exponential growth as a function of the year. The density functional theory was introduced in two seminal papers in 60s. The first was that of Hohenberg and Kohn in the year 1964, which has exceeded 4,000 citation. The second one was that by Kohn and Sham in the year 1965, which has exceeded 9,000 citation. And this following figure actually shows the number of publication where the phrase density functional theory appears in the title or abstract as taken from ISI Web of Science. And as you notice, this data or the statistics is only until 2002, taken about 13 years back. So as you can imagine, there is an explosion of research activity based on the density functional theory, just stressing once again the impetus of this theory. Hohenberg-Kohn theorem consists of two theorems. The first theorem says that the ground state energy E of a many electron system in presence of an external potential Vr is a functional of rho r. The energy functional is given by Ve with the suffix V, which is a functional of density rho, is integral dr Vr rho r plus F, which is again a functional of rho r. This second term F in this right hand side is unknown but universal. It's a function of rho r but does not depend on V. The theorem 2, the second theorem, says that energy is minimized by the ground state density. The proof of the Hohenberg-Kohn theorem is rather simple. Consider the ground states of two n-electron system characterized by two external potentials V1 and V2, which both depend on the space coordinate r. these two potentials, they differ by more than an additive constant. The corresponding Hamiltonians and the Schrödinger equation are then given by the following, these two Hamiltonians, H1 and H2, which has the kinetic energy part, which is given by minus half summation over del I square, and the U, which comes from the electron-electron repulsion term, which is given by half summation I naught equal to J 1 over Rij, and the third term is coming from this external potential, which is different in case of H1 and H2. We thus have these Schrödinger equations, H1 psi 1 equal to E1 psi 1 and H2 psi 2 equal to E2 psi 2. We assume that two wave functions psi 1 and psi 2 yield the same density. Using the variational principle, one can then write the energy E1, which is given by this matrix element of H1 in this basis psi 1, is less than psi 2 times H1 times psi 2, because psi 1 is the eigenfunction while psi 2 is not. Then one can write this thing as psi 2 times H2 times psi 2 plus psi 2, which is a difference between H1 minus H2. So I will have psi 2 times H1 minus H2 times psi 2. Adding these two things, we get back the above expression. So now, since the eigenenergy of H2 is E2, the first term is nothing but E2, and the second term, which is actually involves the difference between H1 and H2, and this difference shows up only in the external potential. Therefore, following the first theorem, the first expression, if you remember, it is given by integral dr rho r times V1 minus V2. Thus, one has the result E1 is less than this expression, which is given by E2 plus integral dr rho r times V1 minus V2. Now, one can interchange the suffixes 2 and 1. By doing that, one would land up into the expression E2 is less than E1 plus integral dr rho r times V2 minus V1. Now, one can sum these two inequalities, and if we do that, the second term in both the right hand sides, they actually cancel each other, and then one is left with this expression E1 plus E2 is less than E2 plus E1. Clearly, this is an impossible situation because it's a contradiction. Thus, we have the following situation. A given rho r can correspond to only one VR. Since VR is fixed, the Hamiltonian and hence wave function is fixed by rho r. We thus conclude energy for a given external potential VR is a unique functional of density. Let us now discuss the minimization of the energy functional. The minimization of the energy functional, which is given by E with the suffix V, functional of rho, is subject to the constraint of normalized density, which is given here. That's integral dr rho r is equal to 1. This leads to the Euler equation for direct calculation of density, as we have also discussed in case of the Thomas Fermi method. Mu being the Lagrange multiplier, then the Euler equation is given by this following equation, where this variation of EV minus the Lagrange multiplier times this constraint gives rise to equal to 0. So taking into account this variation, then this gives delta E over delta rho minus mu equal to 0, or in other words, mu is equal to delta E by delta rho equal to VR plus delta F by delta rho. The goal is to obtain the energy functional, which has the general form as given in this theorem 1, that is E functional of rho is integral dr Vr times rho r plus F, which is a functional of density. Comparing with the energy functional in terms of the reduced density matrix as discussed in the module 21, which was given by energy functional, which is functional of rho little gamma and capital gamma 2, is equal to the kinetic energy functional, the Vne, which depends on rho, plus Vee, that depends on this reduced density matrix gamma 2 plus Vnn. Now one can use the decomposition that gamma 2 that depends on the coordinate r1 and r2 equal to rho that depends on the coordinate r1 times rho that depends on the coordinate r2 times 1 minus F, which depends on the coordinate r1 and r2, where F is the correlation function. One can thus separate out from the electron-electron repulsion term, which is given here as VEE, the classical electrostatic contribution, which is also the Hartree contribution, which is given by half integral rho r1 times rho r2 divided by r1 minus r2 integrated over r1 r2. The crux of the problem is that the exact kinetic energy functional T is hard to compute due to many body effects. Is thus replaced by the kinetic energy of a system of non-interacting particle, which we will show here as Ts instead of T, that is a functional of density, which is the kinetic energy of the fictitious non-interacting system with a ground state density rho. This also leads to the definition of exchange correlation energy functional, which is given by the difference between VEE minus E Coulomb and the contribution from the kinetic energy difference of an interacting system and that of a corresponding non-interacting system. The scheme for obtaining the non-interacting kinetic energy functional Ts for a certain density rho is through the solution of one electron Schrödinger equations, which is shown here and given by minus half del square plus lambda times psi equal to epsilon times psi. For a suitably chosen lambda such that the resulting orbitals yield the same density as given here, which is given here as modulus psi I square summation over I. And then evaluating this functional as Ts is equal to summation over I epsilon I minus integral dr lambda r rho r. The energy functional that is to be minimized for determining the correct ground state density is then given by this energy functional, which has the contribution from the kinetic energy functional, and the other term is EV rho equal to summation over I epsilon I minus integral dr lambda times rho plus integral dr Vr rho r plus E Coulomb plus E exchange correlation. This leads to the variational condition, which should be the variation of this total energy functional should be equal to 0. So it is given by delta epsilon I minus this from the contribution from the second term dr delta lambda times rho plus there is another contribution from the second term which is given by the first term within this bracket, that's dr delta rho minus lambda, and then the contributions from the other term which is given here as Vr plus delta E Coulomb variation over delta rho, delta E exchange correlation over delta rho, and taking into account the contribution also from the second term, that actually leads to the entire expression which is given here by the third term. Now since one has epsilon I equal to minus of psi I times half of delta I squared times psi I plus psi I times lambda times psi I, one can take the variation of this epsilon I, which is given by delta epsilon I, is then the right hand side, you take the variation, and that gives rise to this following different contribution. And these can be written in the following way, which is epsilon I times delta of psi I times psi I, and this term is equal to 0 because we know psi I times psi I is equal to 1 by normalization condition, so its variation should give rise to 0, plus psi I times delta lambda times psi I. One thus has the result that summation over I delta epsilon I equal to integral dr rho r delta lambda r. This in combination with the variational condition leads to this following result, which is given as 0 equal to dr delta of rho r times minus lambda plus Vr plus delta E coulomb divided by delta rho plus E exchange correlation divided by delta rho. Since the variation delta rho is arbitrary, the bracketed quantity must be 0. This gives rise to lambda r equal to Vr plus delta E coulomb divided by delta rho plus delta E exchange divided by delta rho. This clearly shows that if one chooses this lambda chosen by the above expression, the single electron Schrödinger equation leads to the correct density for the system. Let us now discuss the Kohn-Sham equation. The above discussion provides the basis for the Kohn-Sham density functional scheme, which involves solution of a set of n non-linear integral differential equation, which is given by the following, which is given by as minus half del I square plus some V effective times psi I equal to epsilon I psi I. Now V effective, the effective potential, is given by the contribution of the three term. One is the Vr plus integral rho r prime divided by r minus r prime integrated over dr prime plus the contribution from the exchange correlation, which is given by delta E exchange correlation divided by delta rho. The contribution from the first two terms it actually constitutes the electrostatic contribution, therefore given by this phi Es plus the contribution from the exchange correlation. And this contribution, which is basically the electrostatic contribution, obeys the Poisson equation, which is given by del squared times phi Es equal to 4 pi times rho. And the density is calculated as rho r equal to summation over I modulus psi I square. The energy functional in this Kohn-Sham theory is calculated and given in this following way, which is given by E with the suffix V functional of density is equal to summation over I epsilon I minus half integral rho r prime divided by r minus r prime integrated over dr prime plus E exchange correlation, which is a functional of the density, minus integral dr rho r times variation of this exchange correlation with respect to the density. For spin-polarized situation, one needs to include the spin components of the density as the basic variable and rewrite the equations that we have discussed as the following, that we should have EV, which now depends on rho of alpha and rho of beta, which is equal to the kinetic energy term, the Ts, that of the non-interacting electrons, plus integral Vr times rho r integrated over dr, plus the Coulomb contribution, E Coulomb, that is a functional of density, and E exchange correlation, that is functional of density in the up spin channel or alpha spin channel and the density in the beta spin channel. And the Kohn-Sham equations is given by minus half del I square plus V effective, where the V effective depends on the density, which has the suffix sigma, where the sigma is the spin index, which can be either up or down, times the wave function psi, which also bears the spin index sigma, is equal to epsilon I, this energies that also depends on this spin index sigma, times psi I sigma. And the densities, which are the densities for the alpha spin channel or the beta spin channel, is given by, so it has this suffix sigma, is summation over I modulus psi I sigma square. The Kohn-Sham equations needs to be solved by using a self-consistent iterative numerical scheme, which is in the essence of the electronic structure codes, often known also as first principle codes, as will be described in the flow chart in the following slide. So this shows the flow chart for the self-consistent cycle for a density functional theory calculation. One starts with the first principles information. That's why sometimes it is also known as first principle calculation. In the sense, the information one starts with are the atomic number of the elements in the compound or in the system and its crystal structure. One then chooses the initial electron density, which is given by this rho r, and then calculate this effective potential through density functional theory, as we will discuss in the next lecture. That also involves this implementation, a particular kind of approximation for the exchange correlation. And here the exchange correlation normally used, the approximation to this exchange correlation, is the local density approximation, which will be elaborated and discussed at length in the next lecture. So we have this effective potential V effective, which is the contribution from these ions, and then the contribution of the Coulomb term plus the contribution from this exchange correlation part. And once we know this effective potential, one basically solves the Kohn-Sham equation, which is given here, which is minus basically del squared, the Laplace, plus the contribution from the ion, contribution from the Coulomb part, the contribution of the exchange correlation times phi I is equal to epsilon I phi I. This looks exactly like a Schrödinger equation, except the potential part is now way complicated and it depends on the density. These psi's are the Kohn-Sham wave functions, and to really implement it in a computer, one needs to expand this Kohn-Sham wave function psi in some basis. And what kind of basis one will use will be actually discussed at length in the module 24. And from this, one can calculate the new charge density, since we know this Kohn-Sham wave function by solving this Kohn-Sham equation, which is given by rho r is equal to summation modulus psi I square. So this is the new density which can be put here, that we replace this initial density with this new density, and we continue this cycle until and unless the difference between this new density and the old density becomes less than a minimum value. And once this minimum value is achieved, one basically reaches a convergence in the calculation, and one can then calculate the total energy, interatomic forces, stress or the pressure, and the band structure, a number of properties. There are few important observations to be made. Firstly, the Kohn-Sham problem is same as for a non-interacting electron system, in which the electron moves in an effective external potential, which is now a contribution from the three term, the contribution of the potential of the ion, the Coulombic part, and the exchange correlation part. As you can see and probably have realized, all unknown and difficulty is clubbed in the last term, that's the exchange correlation potential, which is given by the variation of this exchange correlation energy with respect to the density. To summarize, we discussed the following points. The Hohenberg-Kohn Theorem was discussed. The evaluation of exact kinetic energy functional is difficult due to the many body effect, as we discussed. It is thus replaced by the kinetic energy of the fictitious non-interacting particles having the same ground state density. We discussed that the contribution of the difference of V electron minus E Coulomb together with the kinetic energy difference between interacting and non-interacting constitute the exchange correlation energy functional. This formalism leads to the solution of a set of nonlinear integro-differential equations known as Kohn-Sham equations. The set of Kohn-Sham equations, as we discussed, need to be solved using self-consistent iterative numerical method. Thank you for your attention.